Okay guys, so we're going to be looking at question 1 from exercise 9G, right? So I thought I'd do this one for you, just to demonstrate to you exactly what's going on, and hopefully you can kind of get an understanding of what we're doing when we're combining the two functions. All right, so if we have a look at question 1, it says find the area of the region bounded by the curve 5 plus 6x minus x squared, and the line x equal to 4 and the line y equal to 5. Right? Remember, the line y equal to 5 is a straight line, it's just horizontal. Okay, it has no gradient, it has a gradient of 0. Okay, so we have to find this area between these two lines basically, and they are also bounded by the x equal to 4 line, right? So from 0 to 4. Now we're going to do this the way we've been doing in the lesson, and then I'm going to show you sort of a different perspective on the same problem, maybe so you can kind of wrap your head around what's actually happening here. Okay, so if we look at this problem, we can say that the area that we're after, okay, is equal to the integral from a to b, and I'm going to call my functions f of x and g of x. I'm going to state which one is which right at the beginning. Okay, so if I have a look at the two functions, okay, I can clearly see that the curve is going to be the top line and this straight line, right, this straight line here is going to be the bottom line. Now they haven't given us the equation on the drawing, but we can work out from the information that they've given us that this is just the line y equal to 5. Okay, so that's the equation we will be using as our second function. Okay, so I'm going to call this y equal to 5 line. That's going to be my g of x. Okay, so if we take the integral of f of x with respect to x, and if you see, if we subtract that area for the integral between a and b of g of x, which is just my straight line, that would give me the area for the shaded region that I want. Okay, so if I take the area of the whole thing and I subtract that little area underneath, I get the area for the tiny portion at the top. Okay, now obviously we could work out the area for that portion underneath simply by doing area. I mean, we know the length and the breadth. However, we're not always going to be given a line, and so we would need a technique if that was a curve, for instance. Okay, now we have made this observation that we've taken the integral of both these functions at the same limit, right? And we learned right at the beginning when we were looking at all the rules for integrals that we can just rewrite this, all right, as one integral, right? We learned it as one integral and we split it into two. Now we are going to take these two integrals and we're going to combine them because they're being evaluated very importantly, right? You can see we're evaluating both of these between the same limits. That's the important thing here. Okay, so we will combine these f of x minus g of x, right? And this is with respect to x. Okay, so we obviously don't have f of x and g of x's. We have equations, so we are now going to just rewrite this formally with our equations. Okay, so we want the area. Okay, this is equal to the integral. Right, now we need our start and our end, so we're going to go to our graph and we're going to look. We can see that the start is going to be the origin, which is just 0, and our end is the boundary. They've told us the boundary line is x equal to 4, so our end will be 4. Okay, we're now going to replace f of x and g of x with our functions. Again, f of x being the top function and g of x being the bottom function. Okay, the top function we can clearly see is the curve. So this is just going to be 5 plus 6x minus x squared, and we're going to take away that bottom function, okay? And this is just y equal to 5, so we're just going to take away 5. That's g of x, okay? Y equal to 5. Right, before we integrate, we're going to simplify the inside of this bracket and just rewrite it neatly. So we have the integral from 0 to 4, okay, and I can see that those 5's are going to cancel out, okay. I have 5 on the inside of this bracket, and this minus 5 is going to cause that 5 to disappear. And so I'm just going to be left with 6x minus x squared. Right? And this is with respect to x. Right? Let's not forget that. Okay, now I'm ready to anti-differentiate. Okay, so this is just equal to, okay, that primitive. Let's find the primitive. We're going to take 6x, raise it to the power 2, divide by 2, and that's going to leave me with 6 divided by 2, which is 3x squared minus x cubed divided by 3. And I would like the area between 0 and 4. Okay, so we're going to state we want f of 4, that's my end, take away f of 0, that's my start. Well, let's plug the numbers in. We're going to be very careful so that we don't lose track of our values. So here's my start. I have 3, 4 squared minus 4 cubed on 3. And I'm going to take away, well, I can see I've got an x in all of my terms, and so when I substitute 0 in there, it's just going to be take away 0. So that's nice and neat. Okay, that just leaves the inside of the bracket, so we can see we have 4 squared, which is going to be 16 times 3, right? So let me grab my trusty calculator here. We have 4 squared times 3, which is 48, and we're going to take away 4 cubed on 3. This is going to be take away 64 over 3, and that will give us 80 over 3, or we can write that as a simplified fraction like that. And remember, this is units squared because we're talking about area. Okay, so there we have found the area. Now I'd like to offer you an alternative view on what we've just done. Okay, and we're going to look at the same problem just from a different perspective. Okay, so let's consider this graph again. So this is the one that I have on the left hand side here. Okay, you can see the green line is the y equal to 5 line, we have the purple lines the x equal to 4 line, and we have the blue curve. Okay, and we want to basically find the area over here. Okay, this is the area that we are looking at finding. Okay. Now, when we were looking at area before, we were looking at these areas bound by the x-axis. Okay, except now we're not looking at it bound by the x-axis. Right? However, if you think about this problem, all right, if you had to move that entire graph, right, down 5 units, right, so if we moved everything here down 5 units, right, what we end up with is the graph on the right. Okay, so my y equal to 5 line has just moved down to the x-axis, right, the whole curve has just shifted down. However, if you have a look, the area that we've asked to find is exactly the same, right? And more importantly, you can see that it's now bound by the x-axis, and this goes back to how we've been solving these problems before. Okay, so let's work this problem from that perspective. Okay, so if I think about the equation, right, I no longer have the same equation for the curved graph, right? This curved graph had the equation y equal to, well, let's go and make sure we don't get the wrong equation. It's 5 plus 6x minus x squared. 5 plus 6x minus x squared. Except if you remember back from your transformations, right, I've shifted this entire graph down 5 units. In other words, I took this graph, f of x, and I subtracted 5 units. This is going to leave me with y equal to 6x minus x squared. very unsurprisingly. Okay, so if you compare this, right, to our combined function, right, just before we anti-differentiated, right, they are obviously the same, right, because in essence we are looking at exactly the same area. Okay, that's why we are able to just subtract that 5, right, and it creates the illusion that we are finding the area bound by the x-axis. Okay, this is also why when we're looking at definite integrals, right, especially between two limits, right, if we're looking at an integral between two limits, that's why we don't have to write Charlie, because you can see it doesn't matter how high or low I move this graph up and down, the area between those boundaries are always going to be the same, regardless of how high or how low I move the graph. Okay, and so unsurprisingly, this will now just be the integral of between 0 and 4, and instead of that function take away some function, we just have 6x minus x squared with respect to x, okay, which is identical to what we did before, right? So that's just an alternative way of looking at this problem, right? In essence, that's exactly what you're doing when you're working out the area between two curves as well, right? You're just combining the two equations. You're taking the top equation and you're subtracting the bottom equation, and that's then giving you an equation to find the area under the new function. Okay, so if you go into Desmos, right, you can actually, when you're working with your other problems, if you want to picture what's going on, you can take the top function, subtract the bottom function, you'll get a different equation. Go into Desmos, you will see that the graph is going to be different to the two graphs you're comparing it, but that new graph will give you the combined area, or the area between the two functions. Okay, so hopefully that helps you with some of the homework questions.